welcome to everybody. A very warm welcome. My apologies for not noticing earlier that today was a very special public holiday, and full marks to those who've joined us live this evening, or in at least one person's case is maybe joining us, but they were up rather late this morning or today trying to photograph the Milky Way. And so they may not actually be awake, but they will be joining us. And before I mention it in any other way, many thanks for all of you who have responded to my email asking for comments about future live meetings and Zoom and so forth. Greatly appreciate that. And we've had quite a useful and diverse set of responses. And I'll say more of that in the gap. This evening, we welcome as speaker our friend, one-time president and now life member of GAS, Dr. Paul Daniels. Tonight, particularly in the context of the James Webb Telescope, he's going to explain about the Lagrange Points, their stability and their usefulness, or otherwise for observing platforms, the Lagrange Points for the Jovian and lunar orbits, and discuss the Kordylewski clouds. Paul gained his BSc in Astrophysics from Queen Mary College, London University in 1978, where he's also been first the secretary and then chairman of the student QMC Astrophysics Society, introducing such luminaries as Professor Ken Pounds, Professor Sir Herman Bondi, and Professor Dame Jocelyn Bell Burnell when she was just a postdoctoral student. He then went on to Sheffield University and gained his PhD, Particle Accretion and the Size, Distribution and Evolution of Cometary Nuclei in 1981. And whilst there, he gave adult education classes in astronomy and became the first ever Sheffield postgraduate student to prepare and give and set and mark exam questions for an undergraduate degree course in astronomy. After a year working on image processing software for the ROSAT X-ray astronomy satellite at the Max Planck Institute for Extraterrestrische Physik in Garching near Munich, he returned to the UK to JWST in Cardiff, left astronomy for a while and worked on the application of image processing in an industrial environment. Whilst there, he also taught MSc courses in image processing and in the Pascal computer language. After that, he moved into computing in the commercial world and in 1988 became a freelance contractor until his retirement a couple of years ago. Around 2000, Paul joined GAS and was soon press-ganged onto the GAS committee after serving for a couple of years as the GAS webmaster before becoming president for the 6 years between 2012 and 2018. He's now an honorary life member. During his time as GAS president, he joined the Council of the Federation of Astronomical Societies and has been the FAS president for the past 4 or more years, 4.5 years, I think. He's also rejoined the Royal Astronomical Society as a fellow and was elected to the RAS Council in 2016 and then elected as one of the RAS vice presidents in 2019. He now lives in Bradenham near Dereham in Big Skies, Norfolk, where the nearest street lights are about 2 miles away and surrounded by oilseed rape, as you'll see from his image. Paul, the floor is yours.
Thanks very much, Nick. Okay, so did I really do all that? Good heavens, that makes me feel very old. So let me start with sharing my screen, just like that. So I'm going to talk about Lagrange points and Kordylewski clouds. Not so much the James Webb Space Telescope, but I will mention it in passing where it's appropriate. I have to blame Professor John Zarnecki really for the subject of this talk, because I'd never heard really of Kordylewski clouds until he happened to mention it once. And so when I saw him last, I said, it's your fault, it's all your fault for getting me hooked onto this subject. So what am I going to cover? Well, first of all, a little bit of basic physics. I did a talk some years ago called May the Force Be With You or something. And so a couple of the slides here are taken from that, but there's a lot of extra stuff added to the end. So some of this stuff is really going to be, I think, fairly basic to you, but potential and force, rotating frames of reference, gravitational forces, and then a discussion of the circular restricted three-body problem and how it leads to the development of the ideas of the Lagrange points. I have actually got a document which gives a lot more of the maths than I'm going to go into tonight, you'll be pleased to know. So if you really are of a mathematical bent, and I'm talking here about GCSE, A-level further maths, stroke first year undergraduate maths, lots of partial differentials and things like that. If you're into that sort of thing, then I've sent a copy of that document to both Martin and Nick as well. So, and then I'm going to discuss Lagrange points in the solar system, more than just the well-known ones of the Trojan asteroids for Jupiter. And then I'm going to go on to talk about Kordylewski clouds and Kazimierz Kordylewski. Okay, so first of all, I'm going to go over this part fairly quickly because it's not really the meat of the talk. But talking about potential fields, so what is a potential field? Well, a gravitational force that's created by two gravitational bodies will have a potential field around it. And electric charges will generate an electric field around them, and similarly magnets will generate a magnetic field. And then there are other potential fields that you may get for the nuclei of atoms, where they will have nuclear fields around them. So effectively, a potential field is an energy level, and if you're going to move something within that potential field by adding or subtracting energy from it, you move something from one potential to another potential. So the most common example of that would be if you bend down to pick something up off the floor. In the process of lifting that mass from ground level to table level, say, you have had to put work into that to change the potential of the thing you've picked up. Similarly, if you have an electric charge in an electric field, then you have to do work to move a charge from one place to another within an electric field. Similarly with magnetic fields, and it's this having to do work that really defines the concept of potential within a potential field. So first of all, with forces, the two most common categories of force are the linear force and the rotational force, a torque. So you have a mass which here you apply a force. If the force is constant and the friction is negligible, then that mass will accelerate at a steady rate according to Newton's laws of motion. Obviously, if you have a static force to overcome, you've got to do that before you can get it moving, and then you've got to overcome dynamic friction. If it's a brick on a plank, you've got some friction to overcome. But either way, you will still, if you overcome those forces, you will still have an acceleration. And then the other one is where you may have a rotating body and you apply a rotational force to that body, and you may accelerate the rotational speed or decelerate the rotational speed of that body. So these are linear forces and rotational forces that we're all well aware of. Every time you go and tighten up a nut using a spanner, you're applying a torque force. So moving on really now to the idea of frames of reference. This is where it starts to get interesting, because whilst having electric charges in an electric field generates real forces, and gravity, a mass in a gravitational field experiences a real force, there are some forces that are there by virtue of comparison of your frame of reference. So if you look here at this first one, you have a man standing in a container, no windows, being pulled along by a train, traveling at a constant velocity or at rest. And because the person can't see outside the train, they have no sensation at all of any kind of movement. If the train's traveling at a constant speed, then still there is nothing moving inside. There is no sense of acceleration or anything like that. If, however, the train accelerates forward and the mass here is on wheels, it'll move to the back, and if he doesn't get out of the way, he gets squashed. So this is an example of the frame of reference of the person inside and the frame of reference outside. The fixed frame of reference causes the mass to want to stay in place because it's part of the fixed frame of reference, but it's on wheels, so it moves within the moving frame of reference, which is the carriage on the train. You have a similar thing here with things that go round corners, and this is your typical white van. And we have, I quite like this explanation. You have a helium balloon tethered to the floor and a carbon dioxide balloon tethered to the ceiling. Clearly, the helium balloon floats and the carbon dioxide filled balloon hangs down. So now we have the white van doing a left turn. It must be driven by a female driver because white van men don't indicate. So as the van is making a left turn, there is now a centripetal force, which is going to cause the air inside the van to move to the outside, to the right in this diagram. And the overall effect of that is rather oddly to cause the helium-filled balloon to move inwards towards the center of the curve and the carbon dioxide-filled balloon to move out. And the way to look at this is to think what's happening to the air. The air inside is being sloshed up against the outside, and the carbon dioxide is still trying to get to where the local, the new modified gravity, effective gravity is, which is a little outwards, and the helium balloon is still trying to float to the new modified upwards. So rather oddly, they do move in opposite directions. But this is an example of centripetal force caused by something that's going around in a circle. And both of these are examples of a difference between perception because of different frames of reference. So the virtual force that's most well known for rotation is the Coriolis force. So what we have here is a carousel with, if you can imagine an observer sitting here in the middle of the carousel, and we have a ball at the center of the carousel. And the observer throws the ball to the right on a stationary carousel. So this is what you would see, and this is what he would see. That ball follows the line out in an easterly direction. Now what happens if the carousel is rotating? Now if the carousel is rotating, as far as anybody outside is concerned, that's us, my screen isn't rotating, that ball has still traveled in an easterly direction. Let me back up again. Whereas if you look at this now from the point of view of the person sitting in the middle of the carousel, what they see is the ball being deflected to their left. So they threw the ball out along a radius of the carousel, but the ball's being deflected to the left. This is an example of a virtual force. There's nothing obvious if you're doing this inside a wall in a room with blank walls, then you have no sense of rotation, apart from the fact that this ball appears to be traveling in a curved path off to the left. That's the Coriolis force. And it's also responsible, for example, if you're firing artillery shells some distance, then they will be diverted from their path by the rotation of the Earth. And if you have bodies of air which are moving in some direction on the Earth's surface, for example, air being pulled into the center of a hurricane where it's forced to rise, that air is also caused to rotate. It's deflected by the Coriolis force. So Coriolis force is everywhere, and I suppose weather patterns are the most obvious way to see that. But we have to take those into account when we do calculations. So here's an example of carousel, and the lady is rolling the ball at just the right speed, clearly with a lot of practice, so that as the ball is about to cross the center, that the carousel is rotating underneath. And so for no obvious reason, this ball looks like it's going around in a circular path. This is an effect of the Coriolis force. So I'm going to move on to talk about gravitational potential, because that's really the subject of tonight's talk, or the core of tonight's talk. This is a static example, no Coriolis force involved. If you were to have two bodies hanging there in space, and the blue rubber sheet is a visualization of what the potential would look like, because you have a gravitational potential around the sun, which is why you have this very long tube down here. This is effectively representing the 1/r function for the gravitational potential of the sun. And this is the 1/r gravitational potential for a planet, the Earth, for example. Clearly, this is not to scale in size or distance. But you can see that a smaller body has a smaller impact on the rubber sheet, that's curvature that's caused by the sun. But this isn't the entire amount of the issue, because you have to take into account the fact that this system is rotating, and therefore Coriolis forces are in play. So the gravitational force is a very weak force. It's the weakest of all the forces, the nuclear force, electromagnetic, etc. And you can see here that it's about 10 to the minus 39 of the strength of the strong nuclear force, which represents the range of the forces that we currently know about. One of the consequences of this weakness, however, is that it does act over very large distances. The nuclear forces don't work on galactic distances, but gravity does work on galactic distances. And so we have galaxies that interact with each other over millions of light years distance. It's an inverse square law, just like electric charge. One of the differences, however, is that there isn't a positive gravity and negative gravity. So gravitating bodies only attract each other. So we have here an example of a small body orbiting a primary. So it's the Earth going around the sun or something like that. But this is an elliptical orbit, so it's not the Earth, maybe an asteroid or a comet. And it starts out down here, going very quickly, and it slows down up here because there is an interchange. As the body here has kinetic energy, where it's traveling quite fast, by the time it gets out to here, the aphelion point, it's slowed down because it's lost some of its kinetic energy to be able to climb up out of that potential well, to exchange one for the other. The total energy doesn't change. The orbit, if you like, has a fixed energy associated with it, provided there are no perturbations or other influencing factors. In the two-body problem, the energy of an orbit stays the same. Similarly, the linear and angular momentum don't change. The momentum is just the mass times the velocity. So again, down here we have a small mass going at a certain speed, and up here we have the same mass going at a lower speed. So your question would be, well, how is the linear and angular momentum of that system conserved? What you have to remember is that in fact they are orbiting about a common center of mass. So even though here the secondary, the Earth, if you like, the comet is moving very quickly down here and very slowly up here, the sun is also traveling in the opposite direction because the two of them are rotating about the common center of mass. So when you take the very large mass of the sun moving by a very small amount into account, again, the total linear and angular momentum of the system stays the same. And the maths of two body systems are relatively straightforward. I wouldn't say trivial, but it wasn't until people like Edmund Halley and so on came along that they managed to calculate the orbits of comets, for example. The maths and the physics were known by then, whereas you go back to people like Johannes Kepler, he knew what happened, but it wasn't based on physics, it was based on observation. So Kepler, for example, had 3 laws, and he came up with the first 2 in a publication in 1609, which is that planet orbits are ellipses, sun at one focus. So we have the sun here and an empty focal point here. The green arrows are the minor axis, and the pink line here is the major axis. More commonly, you measure from the center outwards, so the semi-major and semi-minor axes. So the other one is that equal areas are swept out in equal times. Now, this is pure genius, I think, because it reflects the fact that here, close to the sun, the body travels quite quickly, and out here, it travels much more slowly. And so if it takes the same time to get from here to here as it does to get from here to here, then these 2 shaded areas are the same area, equal areas swept out in equal times. And then his third law is that the square of the period, that's the sidereal period, it's where a body moves from one point back to the same point relative to the framework of stars outside, is proportional to the semi-major axis cubed. If you were to make the orbit 4 times bigger, it means that the period would be 8 times longer. And I seem to have lost one of my cartoons. There's a cartoon of someone saying that they have a caretaker who's very good, but they call him Kepler because he always sweeps the same area every night. Okay, I think you've got to see the picture. Consider now a system of many bodies in space. So this might be a cluster of asteroids or a cluster of dust particles, or may even be a lot of stars in the galaxy. And they're all moving in different directions, in different positions, different directions. So what happens? Well, first of all, the same principle applies as for the 2-body problem. The total potential and kinetic energy of the entire system doesn't change. This is all down to the conservation of energy. And similarly, the linear and angular momentum of the entire system don't change. So it could be that this cluster of bodies are actually rotating, not just translating, like the animation showed just there. But the problem is, whereas you can derive formulae for calculating the position of a planet going around the sun or something like that, the mathematics of many body systems are much too complicated. You cannot, there isn't a formula for it. So you have to do it by literally adding up all of the forces and working out the effects on positions and velocities of every body. So those people, for example, who calculate the dynamics of galaxies, there's no formula, single formula they can apply to do that. They have to do it using a big computer and using numerical means, and that they use some shortcuts. So, for example, a star on one side of the galaxy may be ignored when it comes to its interaction with the star on the other side of the galaxy. So there are approximations that are made. So the many-body problem is much too complicated for a useful mathematical analysis, but it's quite possible to take account of the restricted 3-body problem. And so what is the circular restricted 3-body problem? First of all, there is a primary and there is a secondary and a particle. And the primary has half or more than half of the mass of the system. The secondary has half or less than half of the mass of the system. And the particle is notionally very, very small. So you could think here Sun, Jupiter, dust particle, or Sun, Jupiter, asteroid, or maybe Earth, Moon, and dust particle, as I shall discuss later. The primary and the secondary are in circular orbits about their common center of mass. So if the center of mass of this system were here, for example, then their orbit spinning around that center of mass would be, they would each describe circles about the center of mass. And they're all in a coplanar orbit. So the particle is in the same plane as the orbital plane of the primary and secondary. So it's an approximation to the real solar system, but it's still a very useful approximation. And this document that I've sent to Martin and Nick describes some of the maths, and as part of it, it comes up with this. Now, I'm going to explain what it is, but you don't need to know in great detail what it is. What it says is that the velocity of particles is a function of position, and if we go back to the diagram here, R1 and R2, distance to the primary, and R2 is the distance of the particle from the secondary. R1 and R2 are also functions of X and Y, and mu is the proportion of the mass of the system that's in the secondary. So a small mu, typically for say a planet and the sun, a large mu of a half if the primary and secondary, are the same size. And then it comes out also with a constant that comes out of the maths here. So this is what's known as the Jacobi integral, and it's the starting point for some other things that happen later. In particular, what's interesting is what happens if you say that the velocity of the particle is 0. And I'm talking about 0 here in the rotating frame of reference of the planet going around the sun. So you need to think about the sun and the Earth fixed. They're actually rotating, but we're talking about the particle being stationary in that frame of reference, rotating frame of reference of the sun and the Earth, for example. And here, when you've got the 0 velocity, you can rearrange the equation here, and you can plot a graph of C versus X and Y. So that's where my rubber sheet graph came from, if you like. That was a plot of potential versus X and Y. And so similarly for the Jacobi integral, we can do the same thing. And C turns out to be a potential-like term. So I've written a viewer that you can go and play with yourself here, written in JavaScript and using a free library. And it should work for most browsers, unless your browser is very old. It'll work on Macs and things like that as well. So I'm going to start that up. I'll just click on the link here, and you won't see it until I stop screen sharing. Come back. Go full screen. Do that. Back to here. Screen share to that. So you should be able to see something there. What we've got here is a primary and a secondary, and here you can see that they are of approximately equal size. I'm going to put on some axes here, and the axes here are, if I just tilt it a little bit, you can see an x-axis in red, a y-axis in green, and this blue axis is going to be the axis that I plot my value of C on for a given x and y value. For the moment, all you can see here is the primary and the secondary, although when they're of equal size, it's a moot, I suppose, which is the primary, which is the secondary. But if I modify the value of mu up here, you can see that the relative sizes changes, and also their positions relative to the center of mass of the system changes. So here, with a very small mu value, you can just see this little tiny green dot here. The center of mass is fairly firmly within the primary. So let's give it a little bit more, and I can turn on the same potential surface I showed you. So this is the non-rotating frame, non-rotating surface that I showed earlier. So you can see this is the simple potential without Coriolis force taken into account. What I've got here, what I've done here is I've also added in a sheet, And the sheet, if I change here to look from the side a bit more and I zoom out a bit, this sheet I can move up and down. So it's moving up and down on the blue axis and intersecting with the blue surface here. And I'm not so much interested in the actual numbers. I'm more interested in where the boundaries are between the red and the blue for a given value of that constant. And it produces some interesting results that leads to the Lagrange points. So it's a bit complicated, but it's leading to the one of the parts of this talk. So if I do a top view, so this is looking from the blue axis down on it all, you can see that as I change the position of this sheet going up and down, it reaches a point here, for example, where you've got the sort of the balance point in potential between the primary and the secondary. And the reason I'm showing you this on this simple potential is because it's more interesting when I do it on the surface that comes the zero velocity surface from that Jacobi integral. Okay, so if I switch over to the Jacobi potential here, and I'll just turn this sheet off, you can see here that it has a rather different shape. For a start off, it curves back down again at the edges, whereas the other one just sort of flattened out. And this is the effect of the Coriolis force at distances further out. And you can see here that it's got the same sort of two holes, if you like, in the sheet caused by the two bodies. But it also, if I look from the side, and I need to zoom out to see this, you can see that it's not completely symmetrical anymore. There's a bias caused by the Coriolis force. So I'm going to get some very interesting different patterns when I move that sheet up and down to actually look at where that boundary is between one area and another. Don't forget, this is a zero velocity surface, and that has an interesting implication. So I'm going to do a top view again. So I'm looking again down the blue axis, and I'll turn this sheet on, and I'll take the sheet down a bit, down here. So if I come down here first, at this position, and I'll zoom in so we can see a bit more clearly what's happening. Okay, so we've got the primary here, the secondary here. And this, don't forget the shading on the blue. There's a blue region and the red regions. And what it means is if you have a body here somewhere that's moving in an orbit around the sun, then because this boundary where this intersects is a zero velocity boundary, it means something in here cannot cross to here, because literally it can, if it's going to cross the boundary, it's got to have a velocity. And the whole definition of what I've done is it's a zero velocity boundary. So things that are in here stay in here. Things that are here will stay in here. Things outside will stay there. And things orbiting in the blue region will stay there. Don't forget, this whole thing is rotating, but it gets very confusing when you're trying to point at things that are rotating. So I've got the frame of reference that's fixed on the primary and the secondary, but this thing is rotating in real life. So what happens when I alter the position of this sheet? Well, first of all, at this point, and this is where it gets a little bit tricky, you can get at this point here, where the two red regions merge into one. And this is where the first Lagrange point is. There are other ways of getting three of the points here, but two of them are harder. But this Lagrange point is the first one. This is the first point where things that orbit just here can potentially cross over and orbit into around the secondary as well. If I go a little bit further in moving this sheet out, you get the next point, which is about here. And this is the Lagrange 2 point. And in fact, this is the Lagrange 2 point, is the one where they've sent the James Webb Space Telescope, and Gaia is there. And I'll come back to that one later on. If I go a little further out, whoops, too far. Just here, we have Lagrange 3 point. Some authors label them a little differently, but this ordering is getting to be the more accepted one. You'll notice that I'm moving my sheet in the same direction every time, and it means that the value of C that I'm using is steadily increasing. And so the convention is that you number them in order of the increasing C value. So Lagrange 1 here, Lagrange 2 here, and Lagrange 3 over there. So this is interesting. We now have, for example, the situation where you may have something orbiting here, but it means it can actually move all the way around to here and back again. And things that follow this orbit are following what's known as a horseshoe orbit. And there are bodies in the solar system that follow horseshoe orbits. And again, remember, this whole thing is rotating. So it's the position of the small body, the particle, if you like, relative to the primary and the secondary. So Saturn and one of its moons, or Jupiter, Sun and Jupiter. You do have things that follow horseshoe orbits. What happens when we go a little bit further, and I lift this sheet up a little higher? We get these sort of regions here. And it means something that's moving around here can't get out of this blue region to the red region. Again, it's this boundary, zero velocity boundary. So if something is orbiting here, then it means that it stays orbiting here. And things that follow an orbit here tend to have a rather odd curved shape. And these are known as tadpole orbits. And there are obviously a pair of tadpole orbits that are possible. If I take it a little bit further, try and get this, you can see that I can get here, potentially the very uppermost points of that rubber sheet. What's interesting, if I just zoom in a little bit further here, is that it's really no coincidence that the primary, secondary, and one of these points forms an equilateral triangle. Mathematically, it really is an equilateral triangle, and clearly another one here. This one here is 60 degrees ahead of the secondary in its orbit, and this one here is 60 degrees behind the secondary in its orbit. And this is the Lagrange 4 point, and this one is the Lagrange 5 point. So that Jacobi integral is very interesting because it actually gives you all 5 of the Lagrange points. Okay, so I'm going to drop out of this one now. Stop sharing and go back to my slides. So this is what we had in summary. And you can see different regions here, L1 point here, a Lagrange 2 point here, the Lagrange 3 point here, and Lagrange 4 and 5. So these will crop up later on in the talk. You can also derive to some extent the L1, L2, L3 points by simply looking at the amounts of pull on things. So you've got the sun and you've got the Earth, for example, and you've got Lagrange 1 point, which has a pull towards the sun and a pull towards the Earth. And here, a pull towards the sun and a pull towards the Earth in the same direction. And it's the same over here, a pull towards the sun and a pull towards the Earth, except that the pull here is much, much weaker. The pull towards the Earth is much weaker because the Earth is nearly 2 astronomical units away, whereas here it's much, much closer. The point is, what you're trying to do is to find a point that will be closer to the Earth, sorry, closer to the sun than the Earth is, but still go round its orbit in 1 year. And similarly out here, a point where it's further away from the Earth than further away from the sun than the Earth is, but still goes round in 1 year. So what you're trying to balance here is the combined gravitational pull of the sun and the earth and comparing it with the centripetal force for something at that distance. Now it turns out that for L1, that is 1,482,000 kilometers from the Earth, and it's about 9.91 times 10 to the minus 3 astronomical units. If you're looking outside here, because the sun's pull is a little bit weaker out here than here, there's a very small difference. It's about 10.11 times 10 to the minus 3 astronomical units. And both of these points are used for putting spacecraft, particularly things like solar observers go on the inside because they have an unobstructed view towards the sun. And things out here have an unobstructed view out, looking out away from the sun. The L3 point is a curiosity, but it's only ever found a use in science fiction, where people have postulated that there are civilizations, doppelganger Earths over on the other side of the sun. It turns out that because the pull of the Earth is so weak from 2 astronomical units away, that I've expressed this as 2 plus 0.2 times 10 to the 3 astronomical units is the distance from here to the Earth. So the distance from here to this sort of empty point is only 0.2 times 10 to the minus 3 of an astronomical unit. So it's really only just outside the Earth's orbit at this point here. So you can derive L1 to L2 and L3 from fairly simple non-Coriolis force considerations. L4, L5, you'll have to read that document. It's much more complicated. So one of the other things you have to look at is stability. How stable are things placed at a Lagrange point? And if you remember, the L1 point, the rubber sheet curves one way in one direction, but it curves the other way in the other direction. So it's a saddle-shaped point. L1, 2, and 3 are all saddle-shaped points. What that means is that they are inherently unstable. So if you put a satellite, the James Webb Telescope, at L2, the point where it's been positioned, and leave it, it will wander away from there and eventually you will lose it. What it means is that you have to use fuel to keep things at L1 and L2 at those points. One way of doing it is you can actually add a little extra bit of stability by having the satellite, James Webb, for example, going around in a circle around the Lagrange 2 point, up and down out of the plane of the Earth's orbit in a circular. This is a halo orbit, and a halo orbit means that you actually need less fuel to keep something orbiting about the L2 point than you do if you try and keep it exactly on the L2 point. So that's some of the uses of L1 and L2. But what I wanted to look at here is how much stability is there of these points. It turns out if you do all the maths, you have to have the mass of the primary divided by the mass of the secondary more than about 25. If the secondary is too big, so that the ratio is less than 25, you end up with L4 and L5 not being stable. If the primary is more than 25 times bigger than the secondary, then the L4 and L5 points are stable. And you can have things that will orbit the L4 point or will orbit the L5 point. They become attractors, if you like, for things. And this is where the Jovian Trojan asteroids are. So this table here shows the primary, a sun, or Earth or Mars. So there's different primaries. The sun isn't the only primary in our solar system. And I've taken here the largest planet and the largest or the only satellites of the primary. So that we've got the masses of the primary and the masses of the secondary. And if I divide one by the other, you come up with these ratios. And you can see that in all cases, they are bigger than 25. So this shows that all of the sun and its planets And all of these bodies here and their moons all potentially could have an L4 and an L5 point. If the moon is very small, so its gravitational pull is fairly weak, it won't be a very well-defined point. And you can look at that if you go back and if you go and play with my little simulator, my little viewer, you can simulate that by seeing how flat those tadpole shapes are. Things will wander very easily out away from those. And as you go to slightly bigger bodies, then those points become more well defined. So things like here, Deimos, yes, potentially Deimos can have an L4 and L5 point, but it's a very weak one. So you wouldn't expect to see things captured into Deimos's L4 or L5 points. Whereas when you look at things like Jupiter, for example, this is a fairly good sized body and a decent size ratio. So Jupiter will be very good at attracting things. Going the other way here, we've got our moon. And our moon is only about 3 and a bit times bigger than this factor of 25. So our moon should have L4, L5 points, but not really, really strong ones. Better than Deimos, but still not really strong ones. So you can look at the stability issues for these L4, L5 points as how good they are at attracting things into that part of the orbit. So here we have the view of Jupiter. And you can see here Jupiter has Trojan asteroids, the Greeks, and the Trojan asteroids are the Trojans. They're collectively known as Trojans, but they were named after the Trojan War. And so this is the Greek camp and the Trojan camp. And it happens that they had started naming them before they decided to call them the Greeks and the Trojans. And in here amongst the Greeks, there is 624 Hector, which in fact was a Trojan warrior. And in the Trojan camp here, there is 617 Patroclus, and Patroclus was a Greek warrior. So they each have a spy in the camp. Purely by coincidence, I think, those two asteroids are unusual in that they also have satellite asteroids of their own. So orbiting Hector, there is another small asteroid, and orbiting Patroclus, there is another small asteroid. And I don't think there are many of them that do have orbiting bodies apart from those two. Something else you might notice here is that the Greeks at L4 and the Trojans are at L5. There's quite a difference. There's a 60% difference between the number of Greek asteroids and the number of Trojan asteroids. And in fact, just a quick sort of eyeball assessment here would say, yes, they do look like more Greeks than there are Trojans. It's not really known exactly why that's the case, but it's interesting with something I'm going to come to later on. So here we have other Lagrange points in the solar system. Venus has a body at its L4 point. For Earth, we have these artificial bodies here at the Earth's L1 point. The ones in red are no longer there, and the ones in blue are current. These and the red and blue ones are all artificial satellites, whereas things in black are natural. So we have things like the Soho Observatory that's there, and in fact this one here, ISEE3, became the International Cometary Explorer because they initially parked it at the L1 point, and then realized that with a little bit of a nudge they could actually get it to go and look at a comet. The W map was at the L2 point, which is where JWST is now and Gaia is now. And they're planning more things to go to L1 and L2 because you require relatively little fuel if you're very careful. It's a bit like balancing a ball on the top of an upturned cup. There is a point where you can, if you use a little bit of force, a little bit of thrust, you can keep things balanced on that point. The Earth's L4 and L5 points here This is L4 and L5 points in the Earth's orbit, not the moon's orbit, in the Earth's orbit. There are some asteroids that are associated with the Earth in the L4 and L5 point. And also you've got the two stereo satellites, stereo ahead and stereo behind, for observing the sun, placed ahead and behind the Earth in its orbit. So this is a use of the L4 and L5 points for artificial satellites, for observatories. Mars has points, asteroids or bodies at its L4 and L5 point, often colloquially called the Mars Trojans with a small t, because it's not the Trojans that go around Jupiter or next to Jupiter. Interestingly, these, the L1s and L4, L5, have a different color, which suggests maybe a different origin for them. And Eureka is an interesting one, because it turns out that it has a small body going round it, so it has a moon of its own. It also has a very fast rotation period of, I think, is about 2.8, 2.9 hours. And so one of the suggestions is that these other bodies that are at the L5 point for Mars are bits that have fallen off Eureka, because it's spinning quite fast due to the accelerating action of sunlight falling on the asteroid. The Yorp effect has caused it to rotate faster and faster. And of course, one of its ways to lose angular momentum is for bits to fall off. It's a bit like your ice skater dropping one of the weights or dropping something, and all of a sudden she'll slow down as she rotates. Then we have what I just showed you earlier. We have the Trojan asteroids, Greeks and Trojans for Jupiter. Uranus has a body, Crantor, in a horseshoe orbit, which was the one where it goes from the L4 point round, passing through the L3 point round to the L5 point, and then moving back again. So sometimes Crantor is ahead of Uranus in its orbit, and over a long period of time, gradually it will work its way around to being behind Uranus in its orbit, and then back again. So it literally does this wandering backwards and forwards, being ahead of and then behind Uranus, going round the other side. And similarly, there are a couple of bodies at L4 for Uranus. Neptune has the Neptune Trojans with these bodies here. So there are examples of bodies at L4 and L5 points for other bodies in the solar system. For all of these, the Sun is the primary. Neptune, for example, is the secondary, and these have bodies that are ahead or behind of Neptune in its orbit. So now moving to where something else is the primary. Saturn has here Telesto at the L4 point and Calypso at the L5 point. These are two of Saturn's moons. Tethys is the secondary. Telesto is 60 degrees ahead of Tethys, and Calypso is 60 degrees behind Tethys. Similarly for Dione, it has here Helene and Polydeuces ahead and behind of Dione. So here we have two of the moons of Saturn that have their L4 and L5 point ahead and behind of Tethys and Dione in their orbits. And in fact, with Polydeuces, it follows a fairly elongated tadpole orbit around its L5 point. So coming on now towards the second part of my talk, which is the Earth-Moon system. And we have various things that were tried with the Earth-Moon system and its L2 point. And they're talking about having things at the L2 point, in other words, on the far side of the moon from the Earth, possibly setting a satellite up there where it can act as a relay station for things that are on the surface of the moon on the far side. Excuse me. And for the L4-5 points, a satellite, a Japanese satellite called Hiton, was used to try and demonstrate low energy transfer orbits using L4 and 5. It didn't find anything at L4 or L5 for the Earth-Moon system. But this is exactly where these elusive Kordylewski clouds are that I've referred to. So let me move on now to talking about the Kordylewski clouds. How am I doing for time? Okay. So I've got a half a dozen slides to go, so I'll go through them fairly quickly. So this is Dr. Kazimierz Kordylewski, who was one of Poland's more famous astronomers. He studied, born in Poznan in Poland in 1903 and studied at the University of Krakow. And he became an assistant under Professor Tadeusz Benachowicz. He was a mathematician, Benachowicz, and unfortunately he refused to cooperate with the Germans during World War II and was hoisted off to Germany and imprisoned. And Kordylewski was left in charge of the university at the Jagiellonian University in Krakow. To avoid the Germans coming along and looting the valuable instruments, he buried them under the floor of the basement so that the Germans wouldn't know that they were there. He also came under some suspicion from the Germans, and he hid in his garden in Krakow in 1944, grew a beard. I'm not quite sure that a beard would disguise anyone's face that well. I think if Martin shaved his beard off, we'd still know it was you, Martin. And anyway, he grew a beard to disguise himself, and he managed to avoid being captured. I use the words advisedly here, but in 1945, Krakow was liberated by the Soviets, and Kordylewski carried on working at the observatory. Tadeusz Benachowicz came back from Germany, and he was in charge of the part of the time as well. Kordylewski was very much a family man, and he got married in I forget 1929, I think it was, and had 2 boys, 2 girls. He managed, when he got back to working at Warsaw Observatory, he managed to persuade the Soviets it wasn't a military facility. And he regained possession of the observatory and managed to restore it to use. He was very good, particular. He taught astronomy and mathematics, gave lectures on spherical and practical astronomy and stellar astronomy. He very much had a background of looking at the moon. He's part of the observatory's interest was the moon. And he also was very much involved with youth groups. So he was very good at the outreach and teaching astronomy to scout groups and so on as well. He made a lot of observations on solar eclipses. In fact, if you go and look at his portfolio, he was involved in a lot of things. He had a lot of fingers in a lot of pies. But binary stars and dust matter in the orbit of the moon were particular interests of his. And here, in this picture here, we have Michał Kamiński and Stefan Piotrowski. And these 2 here may well have influenced his decision to go and try and find bodies at the L4 and L5 points of the Earth-Moon system. So he started out initially looking for Trojan satellites, solid bodies at the L4 and L5 points. And he didn't find anything, and following a suggestion by Witowski in '56, he started to look instead for dust clouds, and you can see him here on the terrace of Krakow Observatory, giving a talk about his work. He proposed the existence of these dust clouds, and he claimed to have observed them visually at half the brightness of the Gegenschein. Now, I don't know whether any of you have seen the Gegenschein, but it is very faint. So to claim that you've seen something that is half the brightness of the Gegenschein is going some. But in those days, of course, if you got to a good dark sky site, you had less light pollution then, particularly just after the war. Maybe many places weren't lit up again at that point. And he particularly used a meteorological station that belonged to the university out at a place called Kasprawie Wieś, which is now a tourist resort and ski center down on the Polish-Slovenian border. And he went up there to make a lot of his observations. So particularly in 1956, it would have been very dark up that mountain. So he may well have done. He then continued taking pictures, and from Kasparov, he photographed 2 large faint diffuse patches of light at the L5 point, and then in September of that year he also saw some patches of light at the L4 point. And he declared at that point that he'd discovered these clouds, and being a modest but proudly Polish guy, he wanted to call them Polish moons, or dust moons of the Earth. That didn't really stick, but we did stick with the Kordylewski clouds, dust clouds, KDCs, or libration clouds as the other name. A lot of other astronomers were fairly skeptical that these had been seen, because they said, well, if you've got things there, you've got dust particles there, solar pressure, the Poynting-Robertson effect, the solar wind, all sorts of things will push those dust particles out of the way. You can't get dust particles there. They didn't really believe that he'd actually seen them. There was an American amateur astronomer, J. Wesley Simpson, and they took about 100 photographs of the Kordylewski dust clouds. So it's starting to look a little bit more like there really are dust clouds there. And Simpson claimed that the dust clouds actually orbit the L4 point and orbit the L5 point. So they're not fixed in one spot in the sky, but maybe move around the L4 and L5 points, each one at L4 and L5. So they're going around those points. So he maybe explains, he said, why some people haven't seen them. And he also, along with other people, managed to get onto the Kuiper Airborne Observatory, 12,000 meters altitude, well away from city lights. And they also claimed that they could visually see patches of light at the L4 and L5 points, and they also took photographs. So it's starting to look a little bit like a clincher that these things are there. But there were other people that still couldn't see them despite their work, and Roosen and Wolf here wrote this letter to Nature. I've taken quite a chunk out of the middle, but saying it's disconcerting that the existence of dust cloud satellites at the L4 and L5 libration points, first reported by Coriolis, widely accepted. In other words, they're disappointed that so many people are saying, yes, I can see them, when in fact they've tried hard and they still can't see them. And they finish off by saying, there are many possible explanations of curious patches of light seen in the night sky, and we believe that the Earth-Moon libration clouds are very unlikely. So they rather cast a shadow over this. And here, this is Roosen here, and Wolf here was part of it. They found no evidence. They tried looking for them in 1960, in the mid-60s, and didn't find them at all. Roche, 1975, looked at the Rutgers Orbiting Solar Observatory 6 Zodiacal Light Analyzer, and he claimed to find the Kordylewski dust clouds at the L4 and 5 points, and to see that they are patches of light about 6 degrees across, as seen from the Earth, and moving around the libration points. And again, this is confirming what Simpson had said, that there are patches of light that seem to move close to the L4, L5 point. 6 degrees across as seen from the Earth would suggest that these dust clouds are about 40,000 kilometers across. And then there were other people, oops, missed the last one, other people who've found dust clouds there. They confirmed that they are similar, about half the brightness of the Gegenschein, but also noted that they are redder than the Gegenschein. Now, that may be partly because the dust grains are made of something different to the dust that causes the Gegenschein counterglow, or it may be that the geometry of illumination of those dust grains is different. So, the Huyton satellite I mentioned earlier had passed through both of the L4 and L5 points, and it had a dust impact detector on it. It wasn't its primary mission, but they thought, well, since it's going to go through these, we might as well count dust particles, and it didn't find any change in the number of dust particles. And there have been some more recent papers in 2018, Sliz-Balog and et al. They did some work looking at polarized light in the where the L4 and L5 points would be, and they did detect polarized light, because it turns out that the light from the sun, for the most part, is not polarized. Direct light from the sun, not polarized. But if it scatters off dust particles, it does become polarized. They claimed to detect polarized light from those regions, and they thought that this is probably these dust clouds. There's been a more recent paper, by recent I mean 1st of March this year, by the same people, and they noticed, interestingly, that there are about 3 times more observations, successful observations of the dust clouds at the L5 point than at the L4 point. And it's interesting because this is the opposite way round to the L4 and L5 points with the Trojan asteroids. There are more Greek asteroids at the L4 point than there are at the L5 point, and yet here they're suggesting that maybe there is more dust at the L5 point of the Earth-Moon system than at the L4 point. So they don't quite know why this is, and they've done some numerical simulations, and they found that the L5 point seems to be up to 9% more effective at capturing dust particles than at the L4 point. The dust here they're suggesting comes from interplanetary dust, and it could also be that it's dust from meteor streams that's getting captured at those points. So there is recent work that seems to support the existence of the clouds, but still a lot of skeptical astronomers, even now, there are some that still don't quite believe it. They're looking for other explanations of these patches of light. For example, one of the studies is looking at meteor streams. If you look at a meteor stream tangentially, so you're looking through the stream, because at that point the meteor stream is coming straight at you, they're saying, well, you might actually see scattered light off the meteoroids in the meteor stream. If it happens to be in the right point in the sky, maybe that's what it could be. The calculations seem to show that these points are not very stable when you take solar pressure and other things into account. So some people are suggesting that they may be just transient phenomena. They come and they go. And maybe, for example, when you pass through an interplanetary dust cloud, a clump, it gets captured and the KDCs are visible for a while, and then the dust disappears, which is why some people have seen them and some people haven't. And it turns out that when you look at the equipment that Kordylewski was using, certainly amateurs now have equipment that is at least as good as that. And so if you get a good dark sky sight, you may possibly be able to see the Kordylewski clouds, and it depends very much as well on the sun Lagrange point and observer angle that you're using. So you can see that there is a conflict one way or the other as to whether the clouds are there. They're certainly elusive, not easily seen. What do you think? So that's the end of my talk.
Paul, thank you. Gosh, what a lot to take in. And I realize that I'm always going to be looking at Polish and dust in a slightly different light. Questions from the audience? We have sufficiently. Feel free to unmute and pose your questions directly.
While you're thinking of something, there was an interesting anecdote when Kordylewski was trying to sort of rescue the Warsaw Observatory. This was when the Soviets had just come along and pushed the Germans out. And Kordylewski managed to swap his felt hat for an accordion, which he quite liked and he would like to have kept. But he realized that one of the big problems in post-war Warsaw was a shortage of food, in particular of milk for nursing infants. And so he went to a farm that had been taken over by a Russian farmer. And the Russian farmer, he wanted a cow. The Russian farmer wouldn't let him have the cow. And so he gave the Russian farmer the accordion to play with. And the Russian farmer liked the accordion so much that instead of giving it back, he gave him the cow. and they loaded the cow into a truck and managed to get through all the checkpoints with this cow back into Warsaw. And they kept the cow in the observatory garage for a while to provide milk to the people of Warsaw. He then went away on an observing trip and was rather upset when he came back to find that they'd eaten the cow.
I thought you were going to suggest that he threatened to play the accordion unless the farmer gave him the cow.
Will L4 and L5 then collect more objects than L1, 2, and 3? Is that what we're...
That's right, yes. I made the point that L1, 2, and 3 are inherently unstable, which is why you have to use spacecraft fuel to keep things at L1 and L2. L3 isn't used. Whereas, because if you remember the shape of that that potential curve, the Jacobi integral surface, the L4 and L5 points were right at the very top, and they were actually concave or convex, if you like, in both directions, whereas L1, 2, and 3 were concave in one direction and convex in the other. So because L4 and L5 are a sort of a little well, if you like, it's like putting a marble into a saucer. Things will roll around the saucer and stay roughly in that position. If they were given a big nudge, they might escape and go on somewhere else. But it's a sort of an attractor, if you like, where dust particles or small bodies, asteroids, and so on can collect.
Very good.
And the stability depends very much on that mass of primary to mass of secondary ratio of provided that the secondary is no more than 1/25th of the mass of the primary, then the L4 and L5 points are stable. Otherwise, they're not.
Sorry.
No, Chris, go on.
What explanation, if any, did they have for either L4 or L5 being better at capturing dust or asteroids than the other?
As it stands, nobody knows why the L4, L5 points of either the Jovian Trojans or the Kordylewski dust clouds. No explanations as to why there's an asymmetry. There's enough asteroids at the Jovian L4, L5 points for the statistics, I think, to be fairly clear that there is a 60% difference, and you wouldn't expect there to be a difference. I don't know why, and I'm not aware of any work that explains why there are more Greeks than Trojan asteroids there. And because it could be that there are relatively few observations of the Kordylewski dust clouds, and it may just be that the statistics is poor, or it may be because the clouds are so difficult to see, you have to have just the right geometry. It may be that there's a kind of a bias introduced into the way that the observations are made that may make perhaps observation of one of the Lagrange points harder than the other one. I don't know. I didn't see the conclusion of that in the paper, the recent paper. They don't know why. They said they don't know why it happens. Well, that's the case.
Any other questions? Paul, thank you very much indeed. I'm certainly going to go back and look firstly at the slides you've sent, and they will be available to members. But also I'm going to go back and look at the recording, because there was so much to take in.